A motor controller provides information on how far a motor's axle has turned. In this video, we'll show how to use encoders to control a robot's speed, distance, and turning precision. Here we see a program that causes a robot to move forward by providing 50% power to a pair of motors. The actual speed the motors achieve at 50% power depends on how much friction the robot imposes on the motors, how heavy the robot is, and whether it's traveling on an incline. If one of the drive wheels has more friction than the other, its speed may be slower and the robot may not move in a straight line. We'll make changes that will cause both wheels to move forward at a specific speed, which will help ensure the robot moves in a straight line. Whether you're using the motor controller built into the Rev expansion hub or the separate modern robotics core motor controller, there are several encoder modes available. Two of the modes cause the motor controller to monitor a motor encoder that is mounted on a motor's axle or built into the motor. These encoders produce rapid pulses or ticks as the motor axles turn. We'll use the mode called Run Using Encoder. In this mode, the motor controller uses the ticks it receives from the encoders to determine and adjust the speed of the motors. It uses the power values we provide as percentages of the maximum speed of the motor rather than the actual power levels. The actual speed is calculated for us from the percentage we specify and the maximum speed of the brand and model, which it gets from the information we provide in the configuration file. The motor controller uses the ticks from the encoders to monitor the speed of the motors and adjust the power when necessary to maintain the requested speed. Previously, 50% power brought the motors up to about 80% of their maximum speed, so we'll request 80% of the maximum speed for both motors. The robot will move forward at about the same speed as before, but both wheels will turn at exactly the same speed, and the robot should consistently proceed in a straight line. Another mode provided by the motor controller is Run to Position. When we use this mode, we specify the target position as an encoder tick count. The motor will rotate until the target count is reached. The modern robotics encoder produces 1440 ticks per revolution. Andy Mark Never Rest motors, which have built-in encoders, produce 1120 ticks per revolution instead of 1440. Rev Hex motors, which also have built-in encoders, produce 2240 ticks per revolution, exactly twice the rate of the Andy Mark motors. We changed the mode to Run to Position. To tell the robot's wheels to make 2 full revolutions, we set the target value to 2 times the number of ticks in a revolution, which for modern robotics encoders is 2880, 2240 for Andy Mark motors, or 4480 for Rev motors. To ensure that the encoder values start from 0, we'll reset them by selecting a mode called Stop and Reset Encoder. We place this block above the other Run mode block, so the reset occurs before we set the target positions. Here we see the robot moving forward 2 revolutions of the motor axles. If we want the robot to execute a sequence of steps using motor encoders, the robot needs to wait until the target motor positions have been reached before moving to the next step. We can use a loop that monitors the busy value of each motor. This value will be true until the motor encoder has reached the target position, and then it will become false. Previously, our op mode monitored the run time until 1.5 seconds had elapsed since start was pressed. We'll change this loop to a repeat until that loops until both motors are not busy. We delete the previous loop conditions and have the left side of the AND check the busy value of motor 1 and the right side check the busy value of motor 2. The motor controller will keep the motors on while we're looping, so we don't need to put anything into the do part of the repeat block. After both of the motors have turned 2 full revolutions, the repeat until loop will stop looping. Then we'll make the robot turn. We change the direction of motor 1 and decrease its target position from 2880 to 1440. Then we increase the target position of motor 2 by 1440 to 4320. Remember that the current position of both motors is 2880. So this will change one of the motors to reverse for 1 revolution and the other to rotate forward for 1 revolution, causing the robot to turn in place. Once again, we want to loop until the motors are no longer busy, so we duplicate the repeat until block and place the copy below the new target values. Here we see the robot moving forward 2 axle rotations and turning in place. In this video, we've seen how motor encoders give us the ability to more precisely control the speed and distance that our robot moves, as well as execute more precise turns.